To your other question though about related rates, I think you were imagining, I don't know, maybe. So here's something kind of that I think you're imagining. Like, so for example, if we're given something like, sure, let's see, if r cubed plus x to the fourth plus y to the fifth is equal to, sure, 33. And we're also given that, yeah, yeah, this is gonna be an interesting problem to solve here. See if I can make up some numbers that make sense. Yeah, okay, that's not so bad. Sure. Sorry. Sure, and see if I can make this not suck. Dx dt equals 5 dy dt. I'm sorry, and sorry, apologies. Dr dt equals negative 4. We want to find dy dt when, yeah, interesting. Sure, we'll make it, sure. R equals 1 and x equals, oof, kind of annoying, James. Sorry, I'm trying to make something up on the go here as always. Oh, sure, I'm gonna do that instead. Yeah. Let's 9. Yeah, sorry, R equals negative 2 and x equals the square root of 3. There's a moderately terrible problem. Is this kind of what you were envisioning with the related rates? So let's read this question that I've just made up, which probably might suck, but it's going to be okay. It's still going to get the point across. So we're given an equation. R cubed plus x to the fourth plus y to the fifth equals 33. We're also given some rates of change. But let me make sure I started the Zoom. I think I did. Yeah, okay. The Zoom is on. Yes. Let me do this thing again. And we're given some rates of change. We're given that dx dt is equal to 5. We weren't given any units, so we're just going to not worry about the units. And dy dt, see, dr dt is equal to negative 4. They're asked to find dy dt when r is equal to negative 2 and x is equal to the square root of 3. Okay. So, interesting. Oftentimes, some of the time, you won't have all the pieces of information you need to fill in once you've done the usual steps for a related rates problem. So, regardless of what's going on here, I'm just going to start off the usual way I would write a problem where, well, actually, some of the things are already done for me. So, I'm not going to draw a picture, right? This isn't a geometric or physical situation that can really be drawn well. And they've already given me the equation and told me what I know and what I don't know. So, right, I know what dx dt is. I know what dr dt is. I want to find dy dt. So I'm trying to find dy dt. Well, to me, that says I need to take the derivative of both sides of this equation. So, and with respect to t specifically. So I need to take the derivative of this with respect to t, with respect to t, with respect to t, and also that. So we're going to differentiate both sides of our equation with respect to t. Derivative of r cubed is going to be 3r squared times dr dt. Derivative of x to the fourth is going to be 4x cubed times dx dt. Derivative of y to the fifth is going to be 5y to the fourth times dy dt. And it's going to be equal to 0, the derivative of 33. And now we're going to plug in all the things we know, solve for the thing we don't, except we're going to find that we're lacking, right? Because we plug in for all the things we know. Let's see. So we're going to get 3 times r is negative 2 squared. Dr dt is negative 4. Plus 4 times x is root 3. So 4 times the square root of 3 cubed times dx dt is 5. Plus 5 times, I know I'm trying to solve for dy dt, but I also don't know what y to the fourth is. That's a problem. This is where typically if you're missing something, you have to go back to your original relationship, plug in what you know, and solve for the thing that's missing. So what we're going to do over here is we're going to plug in r equal to negative 2 and x equal to the square root of 3. And assuming, ooh, yeah, okay, yeah, I did the math right. Okay, cool. So I plug that in, look what I get. I get negative 2 cubed plus the square root of 3 to the fourth plus y to the fifth equals 33. So let's see, that's negative 8. What's the square root of 3 to the fourth power? I know all of you can calculate this, just to think about what it's going to be. It's going to be to the second power. So we have 3 to the 1/2 to the fourth. So we have 3 to the second, which is 9. I'm running out of room here. Let's see. So I have negative 1 plus y to the fifth is, no, positive 1. Okay. So right, negative plus 9 is 1. Subtract the 1. You're going to get y to the fifth equals 32. And y is going to be the fifth through to 32, which is 2. So that's what we're going to plug in for y right here. And get a 2 to the fourth power. So sometimes with these related rates problems, you will be missing like one piece of information that you're going to have to go back to the original equation and solve for. Sometimes that's just the way it is. I have another example of this we can do, which is a little bit more straightforward in a minute. Questions about anything before we do the rest, which is the easy part. Or the at least the cognitively easy part. It might look real gross though. Okay, so here's the rest. 3 times 4 times negative 4 is something. It's negative 48, I think. Plus, this is a bummer here. 4 times the square root of 3 cubed. That's just going to be 3 root 3, and there's nothing else you can do about that. So there's your 3 times the square root of 3. So you have 4 times 3 times 5 is 60. So you have 60 root 3 plus 5 times 2 to the fourth. I don't want to do 5 times 16. 5 times 2 times 2 times 2 times 2. Let's do the 5 times 2 first. 5 times 2 is 10. And then the other 2 times 2 times 2 is 8. And 8 times 10 is 80. That's, in my brain, that's much easier than 5 times 16. 10 times 8, way easier. So plus 80 times dy dt equal to 0. So we bring this stuff over to the other side, divide by 80, and we're going to get the dy dt. The thing we were asked to find is going to be positive 48 minus 60 root 3 divided by 80. And yes, I'm sure we could reduce that fraction to some degree, but it's not really the point. Let's look at another problem that's got kind of a similar-ish bent to it. Well, I think, let me see. How do I want to do this one? Sure, yeah, okay. Let's do that. So let's say we have a model plane flies directly overhead at an altitude of 300 feet and a constant speed of, I don't know how fast model planes go. Let's say it's, I don't know, 40 feet per second. That's probably too fast or too slow. I don't know. And 88 feet per second is 60 miles an hour. So that's probably not too terrible to think it's going like 30-ish miles an hour. Sure, why not? 10 seconds after it flew overhead, how fast is the distance between myself and the plane changing? And this is definitely a situation where I would draw a picture. So here we go. Here's me. There's the plane flying overhead. It's going that way. And we know a few things. We know that the altitude of the plane isn't changing. It's 300 feet. However, we know that this horizontal distance it's moving is certainly changing, right? It's going to the right. So how far away it is from being directly above me, we're going to call that x. And also, the distance between myself and wherever the plane is, that's also changing. So here's the plane later. And that distance I usually call z. So x is changing, z is changing. If you wanted to label the height as y wouldn't be changing. Well, I probably wouldn't label. Usually things that are constants, I try not to give them variable names if I know that they're not changing in the sense of the problem. So I wouldn't call that other side y, I would just call it 300 feet. Okay, we've got our picture. We've labeled things that are changing. Now it's our job to identify those things and write down some rates of change. So, what's changing? Well, two things. X, obviously, dx dt, the rate of change that the plane is moving away from me at. Well, they told us, right? It was 40 feet per second. Is it positive or negative? Right. Right. Is X getting bigger or smaller as the plane moves away from me? Oh, it's getting bigger. So yeah, it's a positive rate of change. But it's good to think about because sometimes when you draw these things, like something's moving closer to something else, that rate of change is actually negative for the distance between those two things. So dx/dt is going to be positive 40 feet per second. And we're being asked to find how fast the distance between myself and the plane is changing, which is our dz dt. Um, which we expect to be a positive rate of change because the distance z is also increasing as the plane moves further and further away from me. All right, now we write the equation relating the variables that are up there. And I see a right triangle, I'm thinking Pythagorean theorem. Sometimes it's similar triangles, but that's more like with a cone kind of thing. Here, we want an equation relating x and z, so it's going to be 300 squared plus x squared equals z squared. Yeah, there's a good follow-up question for this problem. Yeah, all right, cool. So, now what? Now what indeed? We've got the equation. We need the derivative, so we're going to take the derivative of both sides. This is where I've often seen people make small errors. What's the derivative of 300 squared? Right, it's a constant. Even though it's something squared, it's still a constant. So you got 0 plus the derivative of x squared is going to be 2x times dx dt. Derivative of z squared is going to be 2z times dz dt. And in the next step where we go to plug things in, we're back in the similar situations we were in the previous problem. We don't know all the things we need to know. We know what x is. X is going to be, oh, do we know what x is? Well, we kind of know what x is. They told us 10 seconds after it flew overhead. So 10 seconds after this plane flew over my head, it should have had a horizontal distance of 10 times 40, which is 400 feet. So you know that x is 400. So you have 2 times 400 feet times, we know what dx dt is. It's 40 feet per second equal to 2 times, we don't have z, right? We're trying to find dz dt, but we don't have this other quote unquote unknown that we need to be able to solve for the thing we're actually trying to solve for. Well, that's where we have to go back to the equation we have, right? We don't know what z is necessarily everywhere. Well, we know we can find z, is what I'm trying to say. We're going to plug in x equal to 400. So we have that 300 squared plus 400 squared equals z squared. And here's where you could do the math, or you could recognize you have a special kind of right triangle. You have a 3, 4, 5 right triangle. It's just a 300, 400, 500 right triangle. So 3, 4, 5, and 5, 12, 13 are called Pythagorean triples. They're often lengths of sides you see of a right triangle that are nice integers. So if you see two sides of like two bases that are multiple, like the same multiple of 3 and 4, like 300 and 400, the third side is going to be the same multiple of 5. Or if you saw like a 6, 8, the other side would be 10. Yeah. Where did I get x equals 400? So they told us that the plane was flying at a constant speed of 40 feet per second. And then they said 10 seconds after it flew over my head. That's where the 400 is coming from. So yeah, so be on the lookout. Like if you see like a 60, 80, that hypotenuse is going to be 100 because those are both just 20 times 3 and 20 times 4, and the third one's 20 times 5. Or you can do the math, right? It's not like it's super hard to do, but it's kind of a pain. But okay, 300 squared is 90,000, 400 squared is 160,000, and you add those together and you get 250,000. And then if that's equal to z squared, then z is going to be the square root of 250,000, which is 500. But we try not to do that work. We don't have to. So then we plug in the 500 here, and then we solve for dz dt. So we get the dz dt is equal to 2 times 400 times 40 divided by 2 times 500, and we should make this simpler. The 2's cancel. 400 over 500 reduces just to 4/5. So we get 4 times 40, so we get 160 divided by 5 feet per second. I guess 160 divided by 5 is something we could calculate. That's 32 feet per second. If dividing by 5 is ever feels like it's challenging, multiply by 2 and then divide by 10. Right, 160 divided times 2 is 320, divided by 10 is 32. Fun tricks for multiplying things and dividing things quickly. So those are a couple of examples of related rates problems where when you get to the part where you're solving for the thing they've asked you to solve for, you might not already have all the pieces you need. And so you'll have to fill them in by going back usually to the original equation. Let's see, was there something else here that seemed reasonable to me to look at? That's interesting. Sure, this was, sure, I'm looking at this homework that's due tomorrow, and I just think this problem looks interesting. So one more, and then we'll move on to linearizations, and then we'll talk about the graphing stuff. So here's problem number 11. Just 'cause I just read this, and like, this looks weird. Suppose, yes, I can. There you go. Suppose that the edge lengths x comma y comma z of a closed rectangular box, meaning it has a top, are changing at the following rates. It always seems weird to me to think about a box where different sides are changing at different rates, but okay, whatever. Changing at the following rates. Let's see, we have dx dt equal to 2 meters per second. We have dy dt equal to negative 3 meters per second. And we have dz dt equal to positive 2 meters per second. Find the following. Find the rates at which the volume, surface area, and interior diagonal, that's a new one for me, are changing at the instant when, I'm going to make up some nicer numbers here, x equals 20, y equals 10, and z equals 15 meters. Okay. So kind of like the first problem we did today, they're giving us a lot of the stuff we usually have to kind of read the problem to find, right? They've given us the rates of change explicitly. They've also told us the things we're trying to find out the changing. We do have to come up with the equations, though. Still worth drawing a picture. Question. Question to think about, not to answer. Which of the things we're asked to find how they're changing, the volume, surface area, and interior diagonal, for which of those does it matter that it's a closed top box? Does the volume care about it being a closed top box? No, the volume's the same whether or not you put the top on it or not. How about the surface area? Yes, definitely the surface area, right? The surface area, the having a lid makes a difference in how much area the box is taking up. Surface area. And the interior diagonal would not matter. All right, let's label these sides in the usual way, X, Y, and Z. And then we're going to start with volume. So for volume, well, the volume equation of a box is x times y times z. And now our job is to do the the differentiating, taking the derivative of both sides. By the way, personal pet peeve, don't say you're deriving it. You're not deriving when you take a derivative, you are differentiating. When you derive an equation, that means you're like discovering or showing like how the product rule came about. So just as a word of wisdom, say differentiate when you mean take a derivative, not derive. All right, so let's differentiate both sides of this equation. On the left side, no problem. We get dv dt like we usually do. On the right side, we have a triple product. Everything matters here, so we're going to use the triple product rule or the generalized version of the multiple product rule, which is just you always get one derivative, I should say each derivative, multiplied by the rest of the not derivatives. So we're for sure going to get a dx dt multiplied by the other two things left alone. We're for sure going to get a dy dt multiplied by the other two things left alone. We're for sure going to get a dz dt multiplied by the other two things left alone. This way of saying it, you get the derivative of one thing multiplied by all the other things left alone, works for the product of any number of things. It's kind of great. And then the rest of this is kind of the dumb part. You're just going to plug in the numbers and find a result, right? Here we're going to get the dv dt is equal to, let's see, dx dt is 2 meters per second times, let's see, y is 10 and z is 15. And it will be meters per second times meters times meters. So it'll be meters cubed per second, which is a rate of change of a volume. Great. And then dy dt is negative 3 times x times z is 20 times 15. And then dz dt is positive 2 times x times y is 20 times 10. And then you get some terrible number, what? 300 minus 900 plus 400. So it looks like it's negative 200 cubic meters per second. That's a pretty fast volume change. So we're losing a lot of volume every second. I take it back. We're losing that much volume per second at that moment, right? Because at different moments, a different rate of change. So at the moment where x, y, and z are equal to 20, 10, and 15, the volume is decreasing at a rate of 200 cubic meters per second. A lot of volume. Okay, so surface area, you guys try. Write the equation for surface area, which is easiest to find by looking at just the picture and thinking about all of the rectangles added together. So it should boil down to each face shows up twice. The XY face you get two of, the YZ face you get two of, the XZ face you get two of. There's 6 sides to this box. And then differentiating both sides, same sort of deal. Got the regular product rule this time. So we take the derivative of 2xy, we're going to get 2 times dx dt times y plus dy dt times x. And then the same deal for the next one. We're going to get 2 times dx dt times z plus dz dt times x plus 2 times dy dt times z plus dz dt times y. And then you can plug in the same numbers. I feel like that's not super duper important, so I'm just going to skip it this time. But you all could definitely plug in the x, y's, and z's and get some terrible gross number at the end. But let's talk about the what was it the interior diagonal length. I'm not exactly sure why they're using the word interior, other than I guess if you said exterior, you might think of like the diagonal of one of the sides, whereas the interior diagonal length is definitely draw this picture again. We're thinking of the length from like that corner back there to that corner up there. I'm sorry, what's that? Which there's a formula for. Although if you didn't know it, it's not too hard to derive. No, no, fine, fine, yes. Okay, so just to point out, if you didn't know how to find this length, you could first find this length here by using the Pythagorean theorem. So this length here, let's call it L. We know that x squared plus y squared equals L squared. And if you want to find this other length, let's call it D. We could say that L squared plus Z squared equals D squared. But then L squared is really x squared plus y squared. So not surprisingly, x squared plus y squared plus z squared equals d squared. Here's what you don't want to do. You don't want to be like, well, I'm trying to find how fast the diagonal length is changing. So I'm going to just say d is equal to the square root of x squared plus y squared plus z squared. You can do it this way. Why make your life harder by introducing a square root? You can take the derivative of both sides of this equation just as easily, more easily, if you just start with d squared equals x squared plus y squared plus z squared. When you're using implicit differentiation, there's no rule about kind of like where you have to start. Kind of like how a week or two ago I was talking about how like instead of implicitly differentiating a quotient, start by multiplying both sides by the bottom so you don't have a fraction to deal with and then do the differentiating of both sides. Same deal here. Start with the easier thing. Here's the attendance form before I forget it. So here, differentiate both sides. Cool. So the derivative of d squared is going to be 2 times d times d d dt. Feels silly to say. And then same on the right, essentially. Each thing squared is going to have the same format of the derivative. We're going to get 2x times dx dt. Oh, I know why they picked those numbers. Ha ha ha. Okay, well, fine. Such is life. We're going to get 2. Well, I assume I know why they picked those numbers. 2y times dy dt plus 2z times dz dt. And now we are going to plug in the things we know. So we know that did I was so close to picking numbers that were going to work out so nice. So well. Oh well. Maybe I did. I don't know. So we're going to plug in x equal to 20, y equal to 10, z equal to 15, and dx dt, dy dt, and dz dt being 2, -3, and 2. So let's see, we have 2 times, oh, d, we'll come back to that, times d d dt equal to, all right, 2 times 20 times dx dt is positive 2. 2 times y is 10 times dy dt is -3. 2 times 15 times dz dt is positive 2. And d over here, kind of like in the previous problems, we have to solve for by using our equation for d. So our d value is going to be d equal to the square root of 10 numbers 20 squared plus 10 squared plus 15 squared. So close, but so far. Oh well. Which is not a nice number, which is probably why they picked different numbers to the actual problem to make it so this value came out to be hopefully not terrible. But even if it is terrible, that's the square root of what? 400 plus 100 plus 225 is 725, which is not a nice square number. So plug that in there, and then your final answer, or dddt, or rate of change of the length of the interior diagonal, is going to be all of this divided by 2 root 725. Let's be smart about this. Let's divide both sides by 2. Then the right-hand side is 40 plus 30 minus 30. So it's 40 divided by the square root of 725. All right, it could be worse. It could definitely be worse. It could always be worse. So again, just to say about related rates, like the process is always kind of the same. You told us some things are changing at a particular moment. You want to find how to relate those things via an equation, differentiate both sides, plug in what you know. Sometimes look a little bit more at the original equation to solve for the other things you might not know in the equation that you need to know, and then finally solve for the one thing they asked you to find. It's definitely worth practicing the process. Okay, moving along to linearizations. So, yeah, let's look at linearization over that. Linearizations. Kind of like how it sounds. It's really just really linearizations for the most part, it's just like the equation of the tangent line and then using it to do some stuff. But really, you've kind of done half of this already. So here's maybe a somewhat typical-ish question for linearization. Let's start with a 1 again. How much does f of x equal to x squared change if x goes from 6, yeah, to 6.2? Well, we could just calculate it. In fact, let's do that first. So the exact change gets a little bit of work. You'd have to calculate 6.2 squared. So our delta f is going to be f of 6.2 minus f of 6, which is 6.2 squared minus 6 squared. That ends up being 38.44 minus 36, which is not impossible to calculate by hand, but kind of a pain, which is 2.44. So that's our actual change in the function value, delta f. But usually, we're trying to avoid doing so much calculation, especially if it's something else that's harder to actually calculate. Like this would be a much harder question to answer if it was how much the square root function changed. Because I don't know what the square root of 6.2 is, and I can't really calculate it very easily. So a reason why we do this. So let's draw a picture because we're going to approximate the change. So here's our nice x squared function. And the idea is we're asking from 6 to 6.2, which I know I've kind of exaggerated here. That's okay. This, what I'm drawing right now, that's representing the actual change. There's your delta f that we just calculated. But what we're going to do is we're going to say, well, it's too much work. Instead, we're going to find the tangent line at 6. So let's draw it about like that. And instead of calculating this much vertical change, we're going to instead say, well, the tangent line does a pretty good approximation of estimating the function value. And so instead of calculating delta f over here and getting 2.44 in this case, we're going to calculate this change instead, which we're going to call, instead of delta f, df. And there's a reason for this, which we'll get to in a second here. So the reason we're calling this df is because, well, here's what we're going to say. We're going to say that the slope of the tangent line, that's equal to your derivative, df dx. And although, again, I know I've said this every time, even though it's not a fraction, we still kind of treat it like a fraction. It's still kind of like a rise over a run. So in this particular problem, we can see that the rise part, the df, is equal to the derivative, let's say f prime of 6, multiplied by the run, the delta x. So our delta f is an approximation of, sorry, our df is an approximation of our delta f. And our df is going to be exactly the derivative df dx evaluated at whatever point we need to. In this case, x equal to 6, multiplied by how much x is changing by, your run. So here's your slope, here's your run, and the run times the slope means the runs cancel out and you're left with the rise. So what do we get here? Well, let's see. Our derivative of x squared is going to be 2x. So it's going to be 2x. We're going to plug in x equal to 6 times our delta x, which is going to be the difference between 6.2 and 6. So we end up with 2 times 6, which is 12, times 6.2 minus 6, which is 0.2. And 12 times 2 is 24, so 12 times 0.2 is 2.4. And that's a pretty decent approximation, right? The actual difference when we go from 6 to 6.2 is 2.44. Our estimated difference is 2.4. Okay, not bad. That's kind of the whole idea, really, is that we're using, instead of using finding the actual function value change, we're using the derivative at this point to help us approximate the change in the function value. It's kind of it. That doesn't mean we can't do a few more examples, but that's the real kind of gist. And yeah, yeah. So let's look at another example. To my mind, there's kind of two ways you can go with this. So we'll do a few of both. So let's look at example number 2. A spherical ball with a 3-inch radius is coated with ice that is a 1/4 inch thick. We want to approximate the volume of ice coating the ball. So a picture just to kind of help us see it. Here's our spherical ball with a radius. Ooh, that's not my best ball picture I've drawn. A radius of 3 inches. And then surrounding this, there's a thin layer of ice going all the way around. Zoom over there. It's not right. So let's talk actual versus estimated. So the actual change in volume, or delta V, would be our bigger volume minus a smaller volume, right? We're just trying to find how much ice there is. It's the volume of the bigger sphere minus the volume of the inner sphere. So it's going to be the volume with a radius of 3.25 inches minus the volume of a sphere with a radius of 3 inches. Okay, and then the volume of a sphere, that's going to be 4/3 pi times 3.25 cubed minus 4/3 pi times 3 cubed. All right. Which is approximately 30.7 cubic inches. Or we could approximate the volume change. So our approximation is going to be, instead of delta V, dV. And it's going to be just like we did before. It's going to be the derivative multiplied by our delta R in this case, right? How much the input's changing by. So it's going to be our dV dr evaluated at the nicer value. We're going to plug in R equal to 3 multiplied by our delta R, how much the radius is changing by. Now, I feel like this example makes a lot of internal sense because our derivative here is the surface area. So you're saying, okay, I'm taking the surface area and essentially multiplying it by the thickness. That seems like it would give you a pretty good estimate of how much volume there was. It's not perfect because the radius isn't always exactly 3, but it's a good estimate. So this is going to work out to be, let's see, our dVdr is 4 pi r squared, evaluated at r equal to 3. Our delta r is 0.25. 4 times 0.25 multiplies to 1, so we're really just left with pi times 3 squared, which is 9 pi. If you plug it into a calculator, that's approximately 28.3. So again, not a perfect answer, but within like good enough, right? If you're asked to estimate how much volume there was of ice, that seems pretty close from my untrained eye. Let's see here. So let's talk about these linear approximations. So, come on. So neither of these examples, I feel like, really give you an example of a linearization. We were kind of using the differential to approximate how much we were off by, but they're still using the thing, we just haven't talked about it yet. So really, what is a linearization or a linear approximation? So linear approximation, also known as, whoops, wow, I didn't mean to cross that out. So that's the underline, just poorly written. Also known as a linearization. Well, it's just the equation of the tangent line. Really, like that's it. It's just written in a way slightly differently. God knows why. I don't really know why we've chosen to do it a different way. Here is an example. Let's say we want to, and I'm going to do this, I'm going to draw this out a little bit. Usually I would just say, do the thing, but here's kind of the process. First, we're going to find a linearization for f of x equal to the square root of x at x equal to, a equal to 25. So the idea is we're taking the square root function, and at the point of interest, 25, we're going to find the linearization, aka the linear function that best approximates the actual function in the vicinity of x equal to 25. Or in other words, the equation of the tangent line at x equal to 25. It's just other flowery words to say the same thing. So this line right here I've drawn, this tangent line, this is our linearization, which typically gets labeled as capital L of x. And you find it in exactly the way you'd expect to find it. To find this line, of this tangent line, we need the usual two things, a point and a slope. Well, we already have half a point. Here our point is going to be x is 25, or a is 25, I should say. A is 25, and the y value, f of a, is the square root of 25, which is just 5. So there's our point. Unsurprisingly, it's 25 comma 5. How do we find the slope of a tangent line? Exactly, we take the derivative. So to find the slope, we're going to take our function f of x equals the square root of x, or as I would maybe write f of x equal to x to the 1/2, and then take the derivative. Our derivative is 1/2 x to the negative 1/2, and then we're going to plug in our point because we want to find the slope at that particular point. So we're going to have f prime of 25 is equal to 1/2 times 25 to the negative 1/2, which is 1/10, right? Because 25 to the negative 1/2 is 1 over the square root of 25, which is 1 over 5. And 1/2 times 1/5 is 1/10. Now, here's the thing you do have to be mildly careful about. Usually when I'm writing the equation of tangent line, I just go straight to, okay, my equation is going to be y minus the y value equal to slope times x minus the x value. Actually, there's two things to be careful of here. First thing is there is an expectation that you isolate y and you use L of x instead of writing y. It shouldn't matter, but it does. So instead we're going to write L of x equals 5 plus 1/10 times x minus 25. Where this 5 here is your f of a, this 1/10 is your f prime of a, and this 25 is your a. Second thing, and this is probably the more important thing, don't simplify this. There's no good to come from distributing the 1/10 and adding the 5 to the negative 25/10. You want to leave this unsimplified exactly as is to answer the type of question that you're usually going to get asked. Because what I really wanted to do to start this problem was say, use a linearization to estimate the square root of 27. This is all the work you would, well, I mean, I've done more work than you here, but really, that's the kind of question I could ask and then expect this work to come out. So if we use this now, we're going to estimate the square root of 27. Well, the whole point of this linearization function here is that this straight line is a really, really good approximation of this square root function at values of x that are close to 25. So what we're going to say here is, well, we know that, and go back here a second, the square root of x is approximately this linearization. So then the square root of 27 is approximately the linearization with the value of 27 plugged in for x. And then we just calculate, we get 5 plus 1/10 times 27 minus 25. This is why you don't want to simplify beforehand. Because when you do this part, it's easier usually if you just plug it in unsimplified. And then we do calculate, we get 5 plus 1/10 times 2 is 2/10. So I would probably write it as 5.2. Or you could write it as 52/10 or 26/25 if you wanted to write it as a fraction. But I do like decimals here if it's easy to calculate because then you can compare it to actually what you get on a calculator. So if you actually go and try to calculate the square root of 27 on the calculator, you're going to get approximately 5.1961. So pretty good. Our estimates pretty close. So let's do a similar question without kind of all of the lead up to see kind of the thought process behind how you would approach a problem like this. At least how I imagine I would ask it if I was a teacher. So, similar idea. Use a linearization. Linear, gosh, long word to spell. To approximate, what do you want to approximate? How about the cube root of 70? Kind of gross, but fine. So, unlike the previous problem, where they gave us what function, told us where to linearize it, and then we did the linearization and then plugged in the right value, they're giving us none of that here. So it is our job to identify the function and the a value. It's not as bad as it sounds. The function is usually pretty easy to identify. Take whatever they're asking you to approximate and replace whatever number is input there with the variable x. So in this case, we're trying to use the function the cube root of x as opposed to the cube root of 70. Not the x root of 70. That I guess technically if there's a number that you could replace, but to replace, hopefully it feels like the more obvious number to get the more obvious type of function that's easier to take the derivative of. So our function f of x is going to be the cube root of x, or if you prefer, x to the 1/3 power. What about a? A should be the closest thing to the number that's there that's easy to evaluate. So before you even answer, what kinds of numbers am I looking to plug into a cube root function? Cubics. Like 8 would be great because the cube root of 8 is 2. So what I'm really going to do is I'm just going to start listing off cubic powers until I get to the one closest to 70. So I'm going to say, well, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. That's probably going to be it, but let's check the next one just to be sure. 5 cubed is 120. Yep, for sure. 64 is the closest one. So that's our A value. But the A is always just the closest thing that's easy to evaluate the function at. So you actually don't have to use a calculator. The rest of this is throwing stuff into this equation of the tangent line, right? It's just the equation of the tangent line. It's just, instead of writing it like we usually do, instead of writing it as y minus y naught equals your slope times x minus x naught, we're writing it as the linearization equals f of a plus f prime of a times x minus a. It's literally the same thing. We've just rearranged it a little, right? Your A is really just what we're calling X naught now. Your F prime of A is just your slope. And your F of A, that's your Y naught. It's all the same pieces, just rearranged and called other names because someone decided it was smart. You know what? I actually know why. I was like, this is the first, yeah, this is really the first time you're making this connection. Sorry. There is a reason why we do it this way that I just realized that I should have known before. It's because this is the format that we like to write Taylor polynomials in, which is something you'll learn about in 21C. So this is the also what's called the first degree Taylor polynomial for a function. And what's kind of cool about Taylor polynomials is that you can add a bunch of powers of x on and on and on, getting higher, higher, and the polynomial becomes a very, very, very good approximation to your actual function. In fact, later on, when you take 21C, you can see how like the sine function has a Taylor polynomial. If you keep adding on terms, it gets closer and closer and closer to being the actual sine function. Same thing is true for e to the x logarithms. So it's kind of neat, but also kind of a pain in the butt. So that's why there's actually a good reason for why you would write it this way versus that way. Okay, I feel slightly justified about that. Usual process. We have the things we want to find. We know what A is. We know what F is. Let's find our F prime. So our F of x is x to the 1/3. F prime of x should be 1/3 x to the negative 2/3. Or I would rather write it as 1/3 times x to the positive 2/3. To me, that just feels easier to deal with. And then I'm going to plug in my A value. So for A equal to 64, F prime of 64 is going to be 1/3 times 64 to the 2/3. And I feel like we've talked about this before, but in case we haven't, whenever you're doing a fractional power like that, you always want to do the root part first. This is 1/3 times the cube root of 64 squared. The cube root of 64 is 4, as we just saw. And then 4 squared is 16, and 3 times 16 is 48. Okay, not the nicest. There's our slope. And I think we have all the pieces now. So our linearization is going to be f of 64, which is the cube root of 64, which is 4, plus f prime of 64, which was 1/48, times x minus a, where a is our 64. This should seem reasonable, right? If we're trying to find the cube root of, what was it? 70? It shouldn't be a whole lot bigger than 4, right? The cube root of 64 is equal to 4. The cube root of 70 should be 4 and a little bit more. This is looking exactly like that, right? We're going to get the 4 right there, plus a little bit more. And if we remember to, and I do think it's good to write this, we're saying the cube root of x is approximately this, because then that helps me just plug in 70 for all my x's and say then the cube root of 70 is approximately L of 70, which is equal to 4 plus 1/48 times 70 minus 64. This actually works out pretty nicely. It's 4 plus let's see, 70 minus 64 is 6. We get 6/48, which reduces to 1/8. So we get 4 plus 1/8, which is 4.125. And just for the heck of it, let's see what 70 to the 1/3 power is. We get, that can't be right. That's 70 divided by 3. That's why you need some parentheses there. At 70 to the 1 divided by 3, which is I want 70 to the 1/3. 4.1212. So actual cube root of 70 is about 4.121285. So pretty good, right? We have the first two decimal places, right? I'm happy with that. It's really, I mean, the degree to which you get this accurate is really just based on the function and the how far apart the number you're plugging in actually is. I feel like there's one more thing I want to say about this before we do too much more. Yeah, okay, yes. So, just to kind of go back to what we were saying before, I'll point out that in this linearization process here, this part here, that's your DF. That's your differential. That's your approximate change going from, in this case, going from x equals 64 to x equals 70. You're changing by approximately 1/8. Actually, you're changing by 0.121285, but that's the part of the differential that we used before, and that's what it is showing up as now. We're just now calculating the whole thing instead of just that one part. There is one type of function I feel like that's especially kind of problematic when you do this. Well, and those are trig functions. So let's look at an example with a trig function. So let's say I want to approximate or estimate, let's see, what's a good example here? Does that one work out the way I think it does? Yeah. Let's estimate tangent of 43 degrees using a linearization. Okay, so usual process. What's our function? And what's our a value? Write down your best guesses for your function and what you think the closest value is to 43 degrees that we're going to plug in. It should be something that you know how to take tangent of, or that you know you're supposed to know how to take tangent of, which I guess kind of gives away the first part. My f of x should be tangent of x. And what's an angle close to 43 degrees that we can take the tangent of and get a nice value out? 45 degrees. What is tangent of 45 degrees? Yep, it is 1. So f of a is tangent of 45 degrees, which is 1. And then we have to find the derivative for our linearization. So the derivative of tangent is secant squared of x. If we plug in 45 degrees, let's see, secant squared of 45 degrees. Hmm. Hmm. It's 2. Is it 2? Here's what I'm really thinking of. I know that cosine of 45 degrees is equal to root 2 over 2. So secant of 45 degrees is equal to 2 over root 2, which reduces just to the square root of 2. And then secant squared of 45 degrees, yep, that's going to be the square root of 2 squared, which is 2. So 2. And now I'm going to rewrite the formula because I like to write the formula when I do this just so I make sure I'm writing the right thing. I know that my L of x is equal to f of a plus f prime of a times x minus a. Honestly, the reason I write it down is so that I remember where the plus and the minus go. Because if I think I'm doing it wrong, I can always be like, wait a minute, does this really look like y minus y naught equals my slope times x minus x naught? Oh yeah, it does, because the y naught's over there. Yeah, okay, cool. That works out. It's a good self-check, I think. If you know the point slope formula for the equation of the line easily, like you've got that memorized, then getting back to there, I think is easy to see. Oh yeah, things are working the way they should. All right, so let's do it. We're going to say that tangent of x is approximately L of x, which is my f of a, which was 1, plus my f prime of a, which was 2, times x minus a, and that's x minus 45. Okay. So I'm about to make a mistake. You might not want to write this down because I'm doing it on purpose. So let's then use this linearization to approximate tangent of 43 degrees. So tangent of 43 degrees is approximately my linearization of 43 degrees, which is 1 plus 2 times 43 minus 45, which ends up being, let's see, 1 plus 2 times negative 2, which is 1 minus 4, which is negative 3. So let's think about this. 45 degrees, tangent of 45 is 1. 43 degrees is pretty close to that. And also, 43 degrees is in what quadrant of the unit circle? First quadrant, where tangent is definitely negative or positive? For sure positive. Like, negative 3 is so far off, we've made a mistake. And the mistake is our units. The mistake is, and I did this on purpose, I was trying to fool you. This is really should be 45 degrees here. This tangent of 43 degrees, 43 degrees. This is 43 degrees minus 45 degrees. This isn't 1 plus 2 minus 2. This is 1 plus 2 times negative 2 degrees, or 1 not degree minus 4 degrees. Yeah, degrees are terrible. Calculus works better in radians. So when you have degrees like this, you want to change that degree to a radian. So what this should really be is 1 minus 4 degrees times pi over 180 degrees. And then the degrees cancel. You get 1 minus 4 pi over 180. And let's just do it that way. Let's say it's, sure, 1 minus pi over 45. Pi over 45 is pretty small, right? It's like, I don't know, 1/15-ish, about 0.06, somewhere around there. Let's actually, okay, fine. I see your faces. Fine. 1 minus pi over 45. It's approximately 0.9301. Whereas if you plug in tangent of 43 degrees, ooh, that's going to be interesting. No, I don't want tangent my answer. Fine. See, so, yeah. Sure. Interesting. Fine, I did want tangent. Problem is my computer doesn't want to do degrees. It's annoying. Oh, it does. Okay, fine. So tangent of 43 degrees is approximately 0.9325. So not a bad answer once we got to the right units. So be careful is all I'm trying to say. If you're asked to do an approximation of a trig function and they're giving you degrees, you almost have to change it to radians. Or at least at some point, so what I really want to point out here is like in the beginning, I definitely wouldn't have changed 43 degrees to radians. That's terrible. Or really even 45 degrees. I would just left it as 45 degrees because I know how to take tangent of 45. That's not a problem. It's when you are multiplying by something with just degrees in it right here, that's where you have to really change to radians. Um, I don't think there's a lot left to say about that. Hmm. Sure. Let me see one here. No, I think that's fine. Sure. All right. We can come back to this if we need to, but we might as well use the last 15 minutes here to talk about moving forward. So, moving forward. Yeah, we'll start there. Let's zoom out a little bit here. Maybe a little bit more. So let's start with what's called the extreme value theorem, which says the following. If a function f is continuous on a closed interval, AB, then F attains an absolute maximum and an absolute minimum. And which occur at either one, critical points, or two, endpoints. A couple pictures that help us imagine what's happening here. So you might have a function defined from A to B that looks like this. Where we have an absolute maximum right here, an absolute minimum right there. The lowest point is at an endpoint. The highest point is at some critical point, which we haven't defined yet, in the interval. Question.
Can 2 points both be the absolute maximum?
Yes, you can have multiple absolute maxima, for sure. For example, you could have a function that looked like this. Where both of these endpoints happen to be at the same highest point, so you have two absolute maxima and an absolute minimum. Or you can have a constant function, which is kind of boring, but technically every point is an absolute maximum and an absolute minimum. Kind of gross. Or you could have the sine function, where you have an infinite number of absolute maximum points. I know it's not on a closed interval, but the sine function does have an infinite number of absolute maxima and an infinite number of absolute minima. Every peak is an absolute maximum. Every valley is an absolute minimum. Or you could have something less exciting, in my opinion, where it looks like this, where you don't have any critical points. Your absolute minimum's over here, your absolute maximum's over here. Just to be clear about what we mean when we say these things, an absolute maximum of f is a value that is larger than all other function values. Phrased more mathematically, if f of x has an absolute maximum at x equal to c, then we can say that f of c is bigger than or equal to f of x for all values of x. Oops, sorry, it's a little tilted there. So your absolute maximum is just where the function has the biggest output. It's bigger than or equal to any other possible output. And the bigger than or equal to definitely includes the possibility of having multiple absolute maxima. And then similarly for an absolute minimum, same kind of idea. So absolute minimum, if f of x has an absolute minimum at c, then f of c is less than or equal to f of x for all x. So one thing we often like to talk about with this extreme value theorem is finding any absolute extrema on a closed interval. Let's look at a couple of examples. Let's start with my favorite example. So let's find, wow, that is the word find, believe it or not. Find the absolute maximum and minimum of f of x equal to x cubed minus 6x squared on the closed interval from 1 to 7. And not that anyone should be asking you to do this for a function that isn't continuous on the interval, but I will note that function is definitely continuous on the interval. So the first thing we're doing, and I know we haven't said these words yet in class, so we'll say now. The first thing we do is we're going to find the critical values. And the critical values of a function are where you have a maximum or minimum, or where you could have a maximum or minimum. For example, a few pictures to kind of, I know we just started this, but a few examples of where you have a critical value, like for example, some pictures of critical values. There's a critical value right there, where the function has a horizontal tangent line. But also, there's a critical value right there, where the derivative is undefined. Where in both of these, you have a potential absolute max or absolute minimum, or a relative max or relative, which we haven't talked about yet. But also, right, you have critical points where you have neither, right? My favorite example of that is the cubic function. This cubic function, you definitely have a place right at the origin where the derivative is equal to 0, where you have a horizontal tangent line right there, but it's definitely not a maximum or a minimum. So critical point is just a place. In fact, I suppose I should write this down instead of just trying to say it a few times. Sorry. So just to say definition, a critical point of f of x is a value x, notably, oh, sorry, in the domain of the function, such that either f prime of x is equal to 0 or f prime of x is undefined. So very generically speaking, a critical point of a function is a place where the function is where the derivative is either 0 or undefined. Now there's a little bit more subtlety there that we'll get to probably on Thursday, but we're not to worry about right now. So back to this question where none of that's a problem. Sorry. Okay. So finding the absolute maximum and minimum of this function on this interval. So the first step is to find the critical points. Find the critical points. Some people call them critical points or critical values. So we're going to take our derivative, f prime of x, which is 3x squared minus 12x, and set it equal to 0. Technically, you should be setting it equal to 0 / thinking about where it's undefined. But we know that this polynomial is differentiable everywhere, so the derivative is always going to be defined, so we're not worried about where it's undefined because it isn't. So we're going to factor. We can factor out of 3x. We're left with an x minus 4. So then we either get x equal to 0 or x equal to 4. And part 2, unlike what we'll do when we talk about finding local maxima or minima or relative extrema, we're going to test our critical values and our endpoints in the original function. And then the absolute maximum is where you have the biggest possible output. And the absolute minimum is where you have the smallest possible output. And that's really it. So it's a pretty straightforward process once you found all the potential candidates. So we have 0, 4, 1, and 7. So we're going to plug all those into the original function. I don't really like the idea of doing 7 cubed though. So instead I'm going to factor this and say, well, my f of x is really, instead of x cubed minus 6x squared, it's going to be easier to deal with if I think of it as x squared times x minus 6. So it's usually if you're plugging in values into a function, it's not a bad idea to factor it first. All right, so let's see. So f of 1 is 1 squared times 1 minus 6, which is going to be negative 5. Oh, okay, I kind of like the change up here. Um, so, something I should point out, 0 is not in play here because 0 isn't in the interval I mentioned. Right, from 1 to 7, 0 is no good. So f of 1 is negative 5. F of 7 is 7 squared times 7 minus 6, which is 49 times 1, which is 49. And f of 4 is 4 squared times 4 minus 6, which is 16 times negative 2, which is negative 32. So there's my absolute maximum. There's my absolute minimum. A couple ways to talk about the maximum. So the absolute maximum is the y value. It occurs at x equal to 7. The absolute minimum is negative 32. It occurs at x equal to positive 4. If you want to write the most information and the least amount of stuff at the same time, you could say you have an absolute maximum of f of 7 equal to 49. You could have an absolute minimum of f of 4 equal to negative 32. That tells you what the absolute max and minimum are, and they also tell you where they occur. Alternatively, you could say you have an absolute maximum at the point 7 comma 49. Absolute minimum at the point 4 comma negative 32. But just be careful. When they're asking you for the where, it is the x part of the coordinate. When they're asking you for the what or the value, that is the y part of the coordinate. How much time have I got here? Not really enough. Um, One other thing I wanted to mention. Uh, we'll save it till next time. I should not try to squeeze in more examples.